Welcome to another of Shore Microsystems Tech Talks. Today we will be discussing MPEG and TSoIP redundancy. MPEG stands for Motion Picture Experts Group, and TS stands for Transport Stream. OIP means that the MPEG information will be transmitted over the IP Internet Protocol. First, a little background on Shore Microsystems. Shore Microsystems has been in the network link protection and redundancy market space since 1994. We specialize in all forms of Ethernet redundancy, most recently with our third generation network protection chassis platform. The new MPEG redundancy features demonstrated today are new capabilities for deep packet inspection of frame content and how that information can be used intelligently to select the most healthy links for connection of high-value protected devices. Now let's spend a few minutes reviewing digital video broadcasting technology. First, the basic method used for decades to move digital video is ASI, or Asynchronous Serial Interface. ASI is a 270 megabits per second raw data interface running over 75 ohm coax cable. The interface is asynchronous with respect to payload data bytes, but constantly active with the insertion of comma fields in the absence of payload data. The system uses an 8-bit 10-bit encoding scheme for synchronization and DC balance that results in an overall net payload data rate of 216 megabits per second or 27 megabytes per second. MPEG specifies a mechanism to packetize the various forms of content, whether it be compressed video, audio, or control information. For all types of content, transport stream TS packets of either 188 or 204 bytes are built containing a payload of encoded data based on the particular content. Each packet consists of a 4-byte header and 184 bytes of content payload. Optionally, a 16-byte Reed-Solomon forward error correction suffix may be attended. The specific content type is determined by packet identifiers, PIDs, embedded in the 4-byte header. It is these PIDs that will be examined by the NPC, the Network Protection Chassis, to determine the MPEG health of the underlying link. Recent market trends are to move ASI to IP and ultimately directly encode TS packets into IP packets. This means gathering multiple TS packets and bundling them into IP packets, with these IP packets usually riding in Ethernet frames. The Network Protection Chassis is specifically designed to handle this form of MPEG data. Finally, this methodology is governed by numerous standards groups, including those shown here. Now we will do a quick overview of the basic Shore Microsystems link protection architecture, and then be able to discuss the new MPEG capabilities built on top of that architecture. This slide shows a typical link protection arrangement. The basic idea is to ensure that a high-value networked device, typically a server of some sort, is attached to multiple access points in a network. The high-value device is called the protected port, and the backbone attachment points are called primary and backup ports. The link protector constantly monitors the health of the primary and backup links and connects the protected device to whichever link is most healthy. In the case where both primary and backup are healthy, then the primary port is given priority. This picture shows multiple instances of this protected primary backup port scenario to handle multiple servers, etc. The thing to note is that up to now, link health has been determined basically by link signal status and optionally traffic, meaning that some threshold of total packets per second arriving from the backbone. The problem in the world of TS over IP is that the presence or absence of certain TS packets can dictate the health of the overall link. So we need a way to look deeper into these packets and see the MPEG streams. This is exactly what is now possible with the NPC. So now let's look at how this works by looking at examples of healthy and failing TS over IP links. This is a traffic flow for a normal case where both links are healthy. First, note a couple of differences from the typical link protection application shown before. First, the Cisco backbone switches are replaced by redundant multiplexers. Second, note that the protected device is now the video stream output, which might be destined for a satellite or microwave transmitter. Now notice the colored blocks above and below the links. These depict a snapshot of different types of TS packets, voice, video, or control, that are multiplexed into IP packets, two of which are shown here. In this healthy example, the upper packets arriving on the primary are identical to the lower packets arriving on the backup. Since both links contain the same data, the primary is selected and the cross-connected to the protected output. Now let's look at a case where there's a malfunctioning video multiplexer. This diagram is similar to the previous example, with the exception that a particularly important PID, called the Program Association Table, is missing in the primary link's stream. The PAT is critical for downstream receivers to decode the remainder of the MPEG stream. So without the PAT, shown here in orange, the MPEG stream is unusable. Notice that the primary link signal is still good, as well as idle traffic logic. That is, there are still the same number of packets arriving on both links. So both would appear to be good using only those indicators. To solve this dilemma, we need the ability to look for and count the arrival rates of specific PIDs. Then this technique could be used to detect the missing PAT and cause a switch to the backup link. Fortunately, this capability is now available in the newly released NPC SM2701CM port card, designed specifically to handle this requirement. So what can we look at now regarding MPEG performance? This slide lists the capabilities of the SM2701CM in November of 2013, and those will likely be expanded. But currently, the system can monitor up to 6 different PIDs per link. The PIDs can be different for primary and backup ports, as well as thresholds. Other errors can be detected, including continuity counter errors, which indicate lost packets, and transport errors, which indicate upstream problems in the encoding. And finally, a monitor mode is supported to allow users to observe received MPEG traffic to verify the presence of expected PIDs before activating any automatic switching logic. So there is significant programmability for user-specified failure modes. On this slide, the first 2 lines show primary and backup link status using the plus and minus signs to represent the link status of up or down. For MPEG, a second set of plus-minus signs indicate the MPEG health of the particular link. Overall, the switching logic can use both the conventional link status and the MPEG status to make the decision on which port is most healthy and therefore switch to the protected device. Notice that the MPEG status for the primary link is marked as down, and that consequently the port is switched to the backup link. We will see what is causing the MPEG status to be down on the next slide. On this slide, we see both the detailed setup and performance of MPEG-capable links. The screenshot is for port 1 from the previous status slide. As shown, 5 of the 6 possible PIDs are configured with identical PIDs and thresholds on both primary and backup. By the way, thresholds are defined as PID arrivals per second. In some cases, it may be useful to establish different failure criteria for primary versus backup PIDs and/or thresholds, but in this case, both are identical. The PCNT and BCNT, primary count and backup count columns, show the PID reference or receive counts from the previous second. Notice that in the last second, all PID receive counts are at least equal to their thresholds, except PID slot 1, which is programmed to the PAT PID. This was the PID that was missing in our failure example shown earlier. So the missing PAT results in a failure of the primary link, MPEG status, and consequently routing of the traffic from the healthy backup link up to the satellite. This monitoring occurs continuously and constantly determines the most healthy link based on the programmed criterion. In summary, it is now possible through the deep packet inspection capabilities of the Network Protection Chassis to intelligently monitor MPEG status in TSoIP routing over Ethernet. The techniques are consistent with TR 101-290 and Pro MPEG guidelines for MPEG performance monitoring. The system is highly programmable in terms of MPEG status definitions. Since this new feature is implemented on the NPC platform, it benefits from other NPC capabilities, including groups, delays, link status switching, and so on. Finally, the new MPEG redundancy capabilities in this Tech Talk demonstrate the power of the Shore Microsystems link protection architecture. That concludes our overview of MPEG redundancy. Please visit our website or contact Shore Microsystems directly for additional information on this Tech Talk or other network redundancy requirements. We thank you for your time and hope you found this Tech Talk useful.